Okay, I think, are we live now? Okay. I will just basically probably start. Good morning, everyone. So thanks for the great opportunity to allow me to present some of my research work in the Science Week. So my name is Wenting Duan. I'm from the School of Computer Science, University of Lincoln. And my main research area is computer vision and medical image analysis. So today I'll talk one part of my research, which is about multimodal image fusion for brain segmentation. So multimodal medical imaging is a research field that has been getting increasing attention in the scientific community in the last few years, especially due to its significance in medical diagnosis. So when we talk about multimodal, it is a widely used phrase in the context of brain imaging studies. It refers to a method in which the image is generated. So different imaging method has different signal source, has different sensors, energy level, spatial and temporal resolution. So they provide different information about the anatomical structure and functional connectivity of the imaged part of the body. And there is increasing evidence that multimodal brain imaging studies can help us provide a more complete understanding of the brain and its disorders. So for example, if it can inform us about how brain structure shapes brain function, in which way they are impacted by psychopathology, and which functional or structural aspects of the physiology could drive the human behavior and cognition. So with the advancement of imaging equipment and digital data storage, we also have a growing availability of these multimodal data sets. Different images are captured by different imaging equipment. So we have a growing amount of multimodal data set for us to have more understanding of the organ of the human brain that we are interested to find out. So, however, the complementary information is usually hidden in these various modalities. That comes for the purpose of fusion, image fusion. So the purpose of fusion is to obtain better contrasted image, better quality, and better visual perception of the image data. Fusion should enable us jointly analyze the multimodal data and leverage the cross information in the existing data. That should be able to allow us to reveal important relationships that cannot be normally detected in a single modality. So that is what the purpose of we want to fuse the multimodal image data. So there are general ways to analyze these multimodal images. So in here, from the picture, you can see that there are we can divide it into 4 groups of strategies. So these strategies are commonly used to analyze the multimodal image. On the left end of the spectrum is what we call visual inspection. So visual inspection is basically about inferring the multimodal information by separately visualizing the results from each modality. And this is the least informative one because you are carrying out everything manually. But it is also widely, extensively used in the medical field. So the doctor probably just look at the CT scan of the patient and then look at MRI and then combine the information with this visual inspection to provide a diagnosis. So it can highlight the different results that provided by each modality, but only in a qualitative manner, which means you manually look at everything and draw a conclusion. Then the second one strategy is about data integration. This type of approach is to analyze each image type separately and then overlay them. But this will only allow for an examination of each type of data that is overlaid to each other. There is no interaction between these data modalities. There is no way you can find out the cross information between these modalities. Then the third type of strategy is asymmetric data fusion. This is to use one data set to constrain another one. So while these techniques are powerful, a restriction is that they impose potentially unrealistic assumption upon the data. So assuming some information will only appear in the boundary provided by another modality, the constraint, the modality you use to constrain the other modality. The error are likely to occur if the modality you used to constrain the other modality contains some noisy information. Okay, so one goes wrong, then the following constrained data also goes wrong. Finally, we have the most recent fusion strategy. It is symmetric data fusion. So this is the approach we focus on in our research. It utilizes and treats multiple image types equally, and we take the full advantage of joint information in multiple datasets. So overall, the use of joint information is only qualitatively used on the far left, and maximum used on the far right. So here is an example to visualize the symmetric fusion approach. Imagine we have a modality that is captured by the brain structure. Then we have another modality that captures the brain function. By jointly visualize using the symmetric fusion approach, this one modality can provide us both of these modalities could provide a joint statistical information that can improve the sensitivity to find out the disease indicators in these statistical analyses of the joint analysis of these two modalities. So in individual, when we are analyzing these modality individually, we cannot really find out these indicators. So this is just one example. Now let's take a closer look at what are the different types of image modality used for brain analysis. The modality for brain analysis can be roughly divided into two categories. So one is the structural imaging, and the other one is the functional imaging. The purpose of the structural imaging is to visualize the various structure of the brain and any physical abnormalities that may affect them. So for example, you can see this type of imaging often include CT scan and MRI scan that is used for detecting tumor, bleeding, blood clots, or birth deformities, this sort of type of disease. Then we have another group, which is the functional imaging. The purpose of functional imaging is to measure activities in certain parts of the brain while it performs certain tasks. So functional imaging is used widely in fundamental research to prove our understanding of the various structure of the human brain. But it is also used for diagnosis. So for example, to diagnose the foci of epileptic seizure, as well as identify prior to the brain surgery, parts of the brain that performs essential functions and must be kept intact no matter what. So these are the two major groups of imaging. So very often, a structural imaging technology may also be used together with a functional imaging technology to better examine the the anatomy and the functioning of a particular area of the brain in a particular individual. So next, we will discuss each type of modality individually and look at how they are used. So the first one is structural imaging, the computerized tomography, also called CT. So the CT, to form CT, we use a series of X-rays of for the brain, for the head, and take it from many different directions. So it will perform a numerical integral calculation on the measured X-ray series to estimate how much of an X-ray beam is absorbed in a small volume of the brain. So in the reconstruction process, from each complete revolution, the computer produces a cross-sectional image of the organ known as the slice. So when you probably hear the doctor often talking about CT slice. So after several revolutions, the computer can sum these slices to produce a 3D image of the target organ. So thanks to the computer, the CT scanner provides doctors with a 3D view of both bone and soft tissue simultaneously. The doctors can then move forward and backwards through the views as they like to perform a detailed examination. And the common use for CT scans are to monitor the patient's progress after surgery, radiation therapy, and chemotherapy, as well as to detect brain tumors, blood clots used in stroke, hemorrhage detection, and other abnormalities. One improvement recently, the latest generation of the CT scanners is move the radiation source around the patient in a spiral pattern instead of a series of separate circles. So this way will generate the images more rapidly and with even better definition. Another common structural imaging that you probably heard a lot of is MRI, the magnetic resonance imaging. MRI uses magnetic field to exploit the physical properties of matter at a subatomic level, and especially in the water, which accounts for about 70% of the mass of the human body. So MRI scans not only provide high-definition images than CT scans, but they can also show sagittal and coronal sections of the brain. CT is only limited to the axial section. So compared with CT scans, MRI scans typically take, the downside is that MRI scans typically take longer and are a lot louder as well. So the contrast provided between the gray and white matter makes MRI the best choice for many conditions of the central nervous system. And we will go into more detail about the MRI modalities because within MRI field, there are also lots of other modalities involved. Now let's look at the functional imaging. Functional imaging, probably one of the most commonly used one is EEG. It's an electroencephalography. Sorry. So abbreviation is EEG. Better to use this term probably. It is a method to amplify the neuronal electrical activities and record the patterns as distinctive signature. So it offers excellent temporal resolution and are relatively inexpensive compared to using fMRI or PET scan, which we'll discuss next. Their spatial resolution is quite poor comparably. So EEGs can help diagnosing epileptic foci, brain tumor, lesion, clots, and so on. So they can also help to localize the sources of migraine, dizziness. It's often used in these sort of condition to diagnose these conditions. There is some sort of image method that's similar to EEG. It's called MEG. So MEG is magnetoencephalography, which is, like the name suggests, EEG records oscillation of brain neurons using electrical fields the activity generates. whereas the MEG use the weak magnetic field. The next one for functional imaging is fMRI, which measures brain activity by detecting changes associated with blood flow. So it is subject to, the subject would watch some visual stimulus, and the fMRI would provide the brain region response and generating an activation map for the doctors or clinicians to see, or the researchers. So it is used to examine the brain's functional anatomy, evaluate the effects of stroke or other disease, or to guide the brain treatment. The last one I'm going to introduce about the functional imaging is PET scan. So it is called the position emission tomography. And this type of scan measure emissions from radioactive labeled metabolic active chemicals that have been injected to the bloodstream. The emission data are computer processed to produce like a 2D or 3D images of the distribution of the chemicals throughout the brain. So the greatest benefit of PET scan is that different compounds can show blood flow and oxygen and glucose metabolism in the tissue of the working brain. The downside is that the image produced by PET scan cannot compete with those produced by fMRI scans in terms of resolution. But as you can see from here, it provides spectacular color contrasts. So the warmer the color present, the more active area of the brain. So it's the doctors would be found it easier to tell which part is active. There is another type of imaging modality that's quite similar to PET scan is single photon emission computed topography. It is similar to PET, but it uses gamma ray emitting radioisotopes and a gamma camera to record data that the computer can use to construct and construct the 2D or 3D images of active brain regions. Now, so overall, these are the common imaging modalities that you probably often heard when you are doing brain analysis. Other modalities include, for example, ultrasound, diffuse optical imaging, also called DOI, etc. But these are less common than the ones we just covered. Now, so what is our focus? Our focus is on MRI modalities. MRI modalities, the focus is on here because it's first of all is commonly used in neurology and neurosurgery. You provide very good detail of the brain. It can cover spinal cord and vascular anatomy. It visualizes these anatomy in all three planes. So we have axial view. So axial view is a series of images you take from below your chin to the top of your head. And then you have the sagittal view. Sagittal view is taken from the one side of your ear to the other side of your ear. And then we have coronal views, which will be from the back of the head to the nose. Okay, so it can. One advantage of MRI is also it has less noise, so there is no beam hardening artifacts compared to CT, and a key advantage, of course, is that it doesn't have ionizing radiation compared to CT. So in terms of physics involved with MRI, we would like to introduce it because there are several aspects of the parameter used in the MRI to introduce about different modalities included in this type of imaging modality. So MRI is based on the magnetization properties of atomic nuclei. So first of all, you apply a powerful uniform external magnetic field to align the protons within the water liquid of the tissue being examined. the alignment is next perturbed or disrupted by the introduction of the external radio frequency energy. So the nuclei return to their resting alignment through various relaxation process. And in doing so, it will emit these radio frequency energy. What happens is that after a certain period of time following the initial radio frequency energy, the emitted signals are measured, and then it is converted into the frequency will be converted using Fourier transform to form the intensity value of the imaging. So there are many parameters involved in while operator sets these settings. So different types of images are created by varying some key parameters associated with the acquisition process. These parameters include what we call the repetition time, TR, which is the amount of time between successive pulse sequences applied to the same slice. Then we have time to echo, which is the time between the delivery of the radio frequency pulse and the receipt of the echo signal. We also have tissue that can be characterized by two different relaxation time. One is called T1, longitudinal relaxation time, which is a measure of the time taken for spinning protons to realign with the external magnetic field. Then we have T2, which is another relaxation time associated with the time taken for spinning the protons to lose phase coherence among the nuclei spinning perpendicular to the main field. And this is called the transverse relaxation time. So based on these parameters, you can obtain different types of modalities. Okay, so the most common MRI modality is what we call the T1 weighted and the T2 weighted scans. T1 weighted images are produced by using the short repetition time. So that is short TE and TR times. The contrast and brightness of the image are predominantly determined by the T1 properties of the tissue. Okay, so the longitudinal relaxation time of the tissue. Conversely, the T2 weighted images are produced by using longer TE and TR times. In these images, the contrast and brightness are predominantly determined by the T2 properties of the tissue. So in general, T1 and T2 weighted image can be easily differentiated by looking at these, looking at the cerebral spinal fluid. Okay, so abbreviation is the CSF. So the CSF is dark as you can see, it's dark in T1 weighted image, and it is bright on the T2 weighted images. A third commonly used sequence in the MRI is called FLAIR. So the fluid attenuated inversion recovery. The FLAIR sequence is similar to T2 weighted image, except that the TE and TR parameters are set very long. Okay, these times are set very long. By doing so, the abnormalities remain bright, but normal CSF fluid is attenuated and made darker. So this sequence is very sensitive to pathology and makes the differentiation between the CSF and the abnormality, makes the differentiation much easier. The last one that I'm going to introduce is the diffusion weighted imaging. The diffusion weighted imaging is designed to detect the random movement of water protons. So as water movement become restricted intracellularly, this results in an extreme bright signal on DWI. So DWI is an extreme sensitive method for detecting acute stroke, which is the application we are going to talk about in our research. And there is a parameter also associated with DWI, which is called the B value. That is associated with defining the gradient strength and the duration of the MRI, which determines the degree of diffusion weighting. Now, so far enough about the different modalities involved for the brain analysis. Now let's move on to other aspects of our topic. Segmentation. So brain segmentation, what is brain segmentation? It is the technique of partitioning an image into several regions based on the feature similarity. So mostly for the clinicians or for the researchers, what really is interesting is to find out what are the major regions. Okay, highlight the major regions of the brain, which is considered of these three major types: white matter, gray matter, and the cerebral spinal fluid. So as highlighted in here. Okay, so segmentation is about trying to find accurately these regions are associated with these three main types of substance in our brain. On top of that, we are also interested to detect and draw which region belongs to, for example, tumor. These are common abnormalities: the tumor, stroke lesion, edema, which is the swelling associated with swelling of part of your brain, or the inflammation. Also, we can also use it to look at the MS lesions as well, which is quite small dots on these scans. So the objective of brain segmentation is to extract these regions and highlight them accordingly as accurate as possible for the to aid the clinicians or physicians to make diagnosis. So due to the variable size, shape, and location of the target tissue, medical image segmentation is one of the most challenging tasks in the field of medical image analysis. So for multimodal fusion-based segmentation, many methods have been developed over the years. Mostly, they are based on here: probability theory, fuzzy concept, belief functions, and then machine learning. So for the method based on the probability and machine learning, different data modalities have different statistical properties, which makes it difficult to model them using shallow models. So for the methods based on the fuzzy concept, the fuzzy measure quantifies the degree of membership relative to a decision for each source. The fusion of several sources is achieved by applying the fuzzy operators to the fuzzy sets. So for the method based on the belief function theory, each source is first modeled by an evidential mass, and then some rules is applied to fuse all the sources. The main difficulty associated with belief function theory and the fuzzy set theory relates to the choice of these evidential mass, and the fuzzy measures and the fuzzy conjunction function. So now let's move on to the machine learning-based type of strategies. Machine learning has some dramatic developments recently, leading to a lot of interest from industry, academia, and even popular culture. These are driven by breakthroughs in artificial neural networks. These are also termed as deep learning. So it is a set of techniques and algorithms that enable computers to discover complicated patterns in the large data sets. So to feed these breakthroughs is actually the increased access to the data. Currently, we call it the big data era. We also have more user-friendly software development frameworks developed, and an explosion of available computing power. So for example, the GPU. All of these enables the use of neural networks that are deeper than ever before. So we talk about the probability theory, how to be monitored by shallow models. Then these deep neural networks is able to provide that sort of deeper layers involved to to extract these complicated patterns associated with the big data that is available to us. So these models nowadays form the state-of-the-art approach to a wide variety of problems in computer vision, language modeling, and robotics. So same trend happened for medical segmentation. You've seen lots of literature in the segmentation field. So in this talk, we will put our particular focus on the deep learning-based multimodal fusion for brain segmentation. So deep neural networks learns feature representations from the data automatically in an incremental way. So that's why you see here, there are lots of layers. You go into the first layer and then move on. So this is to extract feature from low level to high level incrementally. So the first several layers extract low-level features, such as edges and gradient orientations appeared in the image. Then, with more layers added, high-level details such as shapes and textures of the interested region are learned by the network. The network can extract complex hierarchy features from a large amount of data by using these layers. So that was the basic framework of a deep neural network. So the deep neural network-based fusion strategy for segmentation can be roughly divided into 3 groups. The first group is input level fusion. So what do we mean by input level fusion strategy? Imagine we have 2 modalities. One is CT, one is MRI. Then these at input level, the fusion happens like this. It was concatenated channel by channel at input level, then feed into this neural network to learn a unified image feature set. So what happens is that it assumes a linear relationship between different modalities when there will be some sort of correspondence between these modalities that can be nonlinear. However, this is a widely used applied strategy. People simply, when they are dealing with multimodal fusion, they simply just concatenate these models, these images all together as putting it into a single volume to for the neural network to learn. The next group of strategy is based on the output level fusion. So for the output level fusion, what happens is that each model has its own segmentation network. Okay, so each modality image is used as a single input for a single segmentation. The single network exploits the unique information of the corresponding modality. The output of the individual network are integrated to get a final segmentation. So the fusion happens at the output level. This is usually done by what we call voting. So there are 2 types of voting strategy. The one is the averaging strategy. The other one is majority voting strategy. For average voting strategy, the networks are trained separately, and then it generates what we call a confidence probability map. Then what happens for each modality, there is a confidence probability map, and it's about average these probability map, and then the final segmentations are obtained by assigning each voxel with the highest confidence, so highest probability. So there is also another voting strategy is called the majority strategy, which, like the name suggests, the final label of the voxel depends on the majority of the label of the individual network. Okay, label fusion. Each modality has its own individual network path. So CT has a network path on the top, and then MRI has a network on the bottom. So features are learned by each individual path, then they are fused within this network. Okay, they are connected to each other and they share some sort of correspondence. So the fused result is fed to the decision layer to obtain the final segmentation result. This can effectively integrate and fully leverage the multimodal imaging. So in comparison to the strategies mentioned previously, where fusion happens either at the input level or the output level, some recent works has already proved that performing fusion within the convolutional feature learning stage instead can generally give better segmentation results. So our focus is on the leisure level fusion. So we talked about these fusion paths. What about the network architecture? So for the network architecture in deep learning, there are many types of architecture exist. So probably some of you who is in this area already heard of VGG, ResNet, DenseNet, and in medical field, most often used is UNet. So one avenue, as you can see, one avenue of the research on multimodal fusion is based on DenseNet, where the feature reuse is induced by connecting each layer with all the previous layers. So you can see that once feature extracted, the features are concatenated in further layers, in deeper layers, to propagate these features in a more efficient way. So in particular, we identify one type of network called hyperdense net. Hyperdense network developed recently. It is developed recently, and it extends the dense net so that the dense connection not only exists in the layers of the same modality, but also between the modalities. So you can see that this, for example, this particular feature map has been concatenated to the other modality in the first path, and the feature map generated in the top path has been concatenated in this path in the second path as well. So it's interchanging these feature maps to learn a better understanding of the fused features. So this type of network has made significant improvements over the state-of-the-art segmentation techniques, and it has been ranked first for 2 highly competitive multimodal brain segmentation challenges. So that's why we have our focus on the hyperdense network. However, we also identify the limitations with this type of network. So for this kind of network, the feature maps from all modalities as well as previous layers are simply fused using concatenation, as you see from here. It's basically stacked together, okay? So that the dense connection not only exists in the layers of the same modality, but also between modalities. We speculate this type of approach fails to consider the discrepancy in visual features under different modalities, and the importance of model-specific learning, so resulting in some ineffective multimodal feature merging and propagation. We also think that it can introduce redundancies when you are just simply stacking them in different layers, when early features are not needed in the later layers. So when they are stacked together, the fusion strategy is not really exploiting the relationships between these feature maps. So our current research focus lies on exploring the optimal fusion point and trying to reduce the redundancies existing in this network. We also exploit better feature fusion strategy rather than just let them concatenate and stack them together. We test this type of fusion network for 2 types of applications. One is infant brain segmentation, and the other one is the stroke lesion segmentation. So far, we've made 2 major developments. The first development, exploiting optimal fusion point within the network. And we look at what is the best way to fuse, what is the best layer to fuse these feature maps from different modalities, so that we can also, in a way, reduce redundancies in the network. So we carried out experiments on acute stroke lesion segmentation with 3 modalities, and we also carried the experiments on iSeg17 infant brain segmentation. These include, this data set has 2 modalities. So testing with different types of modality combination as well. So in the first one, it has T2 and B1000, DWI B1000, DWI B0. For the infant one, we have, I think, T1 and T2. So This achieved competitive results compared to the state of art. With we not only achieved about slightly improvement to the hyperdense network, but we have managed to reduce 1.2 million less parameters, reduce 1.2 million parameters associated with the original network. So results in this table has shown the proposed network yield better segmentation results and with less parameters. The next development, other development we involved in our research is to have better integration of layer features. For this, we propose a new way of fuse features from different modalities in a densely connected architecture. So we proposed a raised fuse module that is introduced to replace the simple concatenation fusion used in the best network. And we evaluate, you can see clearly how our proposed network has converged better and also produce higher segmentation accuracy. So the experimental results demonstrate the effectiveness of our proposed network and its capability of tackling challenging multimodal segmentation tasks, such as on this one, which is the stroke lesion segmentation, and on this one is the infant brain segmentation. So this is all of my talk, and I hope I have managed to provide you with some insights to multimodal fusion in brain segmentation, as well as my current research work. Our research group, Laboratory of Vision Engineering, is always keen to collaborate and welcome students who are interested in this kind of research to join us. Thank you, and questions, please. So, okay, I can't really. If there is no questions, then thank you very much, and I hope you have a good day. And it's sunny outside. I hope you enjoyed the talk. Thank you.